Welcome to this second tutorial of the European GNU Radio Days dedicated to multi-channel analysis of the various signals found in the baseband and how to best use external tools to complement GNU Radio and select the most suitable tools to reach an objective. Here is the outline of the presentation. We remind the basics of SDR architecture. We demonstrate multiple signal analysis on broadcast FM station and extend the demonstration to POXAC, the pager protocol. Then we show how we can analyze multiple ACARS channels, ACARS being the protocol for communicating between aircraft and airports. We show how digital processing can solve IQ imbalance issues as well as local oscillator leakage with a demonstration with a scientific instrument. And finally, we conclude with 0MQ UDP-like streaming applied to radar systems and a demonstration with correlation comparison between GNU Radio and GNU Octave. So for getting started, let us remind the basic architecture of software-defined radio receivers. The ideal architecture would be an antenna connected to an analog to digital converter and all processing being performed in the software level. This will differ from the current hardware architecture where all elements are implemented as hardware processing parts and fixed parameters are implemented during assembly. And the current software-defined radio architecture will feed a radio frequency signal not directly to an analog to digital converter because of its limited resolution at high radio frequency signal and the loss of dynamic range if a strong interference lies between 0 Hz and the sampling frequency of the analog to digital converter, so that an initial frequency transposition is performed by a local oscillator. This is a hardware level. Data is sampled as a sampling frequency fs, and all further processing is completed in the software level. So this means that after transposition, we start from a signal centered on the local oscillator, and following acquisition, we will acquire a signal that ranges from minus the Nyquist frequency to plus the Nyquist frequency centered on 0 Hz. And the discussion of today's tutorial lies in the fact that multiple channels or multiple spectral components might be found within this bandwidth. So our objective will be to try to process each one of these spectral components simultaneously in parallel by bringing each one of these components centered on 0 Hz, centered on DC. So this means that once the data has been sampled using the A to D converter, we need to transpose the signal to bring it centered on 0 Hz. So this means that we will mix each one of these spectral components at F1 or F2 by this time a software-defined radio oscillator. This is called a numerically controlled oscillator, an NCO, at frequency F1 or F2, and this output signal will be centered on 0 Hz. So this will bring the signal from F1 or F2 centered on 0 Hz, and this signal can be analyzed to extract its information content. However, imagine that another spectral component is lying in this region over here. Then by moving this spectral component to center 0 Hz, then by assumption of the periodicity of the spectrum, this spectral component will be shifted by the same amount, and so will this spectral component. So we will end up with this blue spectral component shifting by aliasing to the negative frequency band, and this spectral component here will move to the positive range over here. And these two spectral components must be eliminated prior to processing this center frequency here. So some filtering will be applied, and this filtering will be a finite impulse response filter. So these are the basics of multi-channel analysis, bringing each signal centered on 0 Hz and filtering unwanted spectral components. One last item is that when sampling n samples and data in the time domain because of a one-to-one relationship between frequency and time domains, then when we sample over this sampling band of fs, the sampling frequency in the frequency domain, the n samples that were collected, because when we collect n samples in the time domain, they will lead to n samples in the frequency domain, then the bin width, or the spectral resolution of the Fourier transform, will be delta f equal to fs over n, the sampling frequency divided by the number of data that were analyzed. So this will define how many data must be analyzed when aiming at a bin width of delta f. And also, if we define some sort of spectral analysis leading to resolution delta f, then this tells us how many taps, how many coefficients in the FIR filter will need to be identified. So let us discuss practically this consideration in the case of analyzing multiple broadcast FM stations. In this example, we will consider the frequency band of the broadcast FM centered on 96.9, and because multiple stations are located adjacent to the center frequency with this 1.5 megasample per second and the typical spacing of FM stations of 400 kilohertz, we might expect 3 or 4 broadcast stations within the sampling frequency. So what we can try to address is, if we have this 1.5 megasample per second bandwidth, so this is fs of 1.5 megasample per second full range, base band sampling band. Then if we have 2 stations, and we will see actually that we might have 3. We have centered on the broadcast station we wish to listen at, and then we've got adjacent FM broadcast station that we might listen to. Now, this frequency transposition step that we discussed earlier, where we have sampled using the ADC at sampling rate fs, and then we wish to switch the center frequency using either f1, f2, the offset frequency over here, and then filter out any unwanted spectral component. This is such a common feature in software-defined radio that GNU Radio provides a ready-made block for doing this, the Frequency Translating FIR filter. The Frequency Translating FIR filter will provide the options of a center frequency. This is this local oscillator frequency here by which the signal will be transposed, and the taps, which are the coefficients of the low-pass filter that will be used to eliminate all the unwanted spectral component. Now these taps, these weights of the finite impulse response filter, are defined by these low-pass filter taps blocks. Remember that a FIR filter, a finite impulse response filter, is defined with an output at times n equals to the weighted sum, the sum of past inputs, x. So we have a convolution which is written as sum of bk x n minus k, with the b here being the taps. One particular case is if we consider that an output at a given time is equal to the input at this given time and no contribution of a pass value. This means that the weight b0 is equal to 1, and all the other weights bk for k greater than 0 will be equal to 0. And this particular case is the identity where we have an output equal to the input. And in this case, whatever spectral component was shifted during the spectral transposition will be kept in the output spectrum, and we are just rotating along the x-axis the spectrum. So in this example here, we see that we have one low-pass filter to select the center station, here 96.9. This center station has been selected and is decoded using the wideband FM receiver here. And on the other hand, we're going to bring another station that is located minus 107 kilohertz from the center frequency. We'll bring it center on 0 hertz and run the wideband FM receiver on this new channel. Now we have multiple decoded outputs. We can either select to listen to one or the other channel. Here we have a weighted sum of both contribution that will feed the audio, the sound card. Now this capability will be limited by the bandwidth. The number of stations found is defined by the sampling frequency fs and hence the bandwidth that we have acquired. The wider the bandwidth, the more sample to be processed, the more computational power is needed. And furthermore, we can only analyze as many channels as we have central processing units. So at some point, if we have too many of these wideband FM receivers, we will run out of computational power. For example, the Pluto SDR, with its very wide bandwidth, more than 10 megahertz, can sample many FM stations. However, the quad-core CPU of this i5 laptop can only handle up to 8 wideband FM decoders simultaneously. This is demonstrated on this movie of the Pluto SDR recording 8 stations simultaneously. So let us demonstrate this concept practically. So here is an example of GNU Radio running a single FM station receiver, and this single FM station receiver is now complemented with this frequency sync. We see here the center FM station, and here we have the adjacent FM station. So what we want is to bring this new FM station that we just seen on the side of the spectrum to the center frequency. To do this, we will use this frequency translating FIR filter, and what we bring is the minus 700 kilohertz frequency offset from the side station with taps unity, and on the frequency sync we will display both channels prior and after to frequency transposition so we can see the difference. So when running this spectrum analysis, we see on the center 0 hertz here that the old initial station is centered and the station that was here on the side has been brought to 0 hertz. So both stations are now ready to be demodulated. We already have a first demodulator on the frequency that is centered on 96.9. So what we need now is to filter out this initial station so that the sideband becomes dominant. So we create a low pass filter. Here we have fixed the low pass cutoff frequency, and these taps, these coefficients, will define the properties of the low pass filter that is applied at the frequency translating FIR filter. So now we check that only the stations that we are interested in are left, and surely enough, the initial station is dominant, but after filtering, the shifted frequency station is strong centered on 0 hertz. So we copy the wideband FM demodulation block and we insert it after the frequency translating FIR filter, making sure to properly decimate. Again, the frequency translating FIR filter will allow you to get rid of the unwanted spectral components by decimating and getting rid of all the unwanted spectral parts and reaching the targeted bandwidth of 8 times 4 times 48 kilosample per second, which was the bandwidth, the sampling rate that we selected initially. And what we will do is we will weight each one of these outputs so we can either listen to one station, the other station, or a weighted sum of both. So we introduce a multiplication by a fixed weight that will be tunable. We do so for the second station as well, which will be weighted by a factor of k between 0 and 1. And the second station will be weighted by 1 minus k, so we can jump from one station to the other. So we sum the two audio components before feeding the audio sync here, and we assemble all these blocks to create the full processing chain. To allow for dynamically tuning the weight of each of the channel relative to the other, we create a slider with this variable k ranging from 0 to 1 with step 0.02, so we can finely tune the relative weights. And we run this flowchart. So here we have both stations. Left station only. Right station only. Both stations again. First station. Second station. Both stations. So with this, we demonstrate how we can receive two stations simultaneously and analyze multiple data streams available within the sampling frequency. So again, remember, the most important aspect is that whatever signal can be found within baseband, so after bringing the radio frequency signal to the area centered on 0 Hz, all these signals that we saw earlier, so we had 3 FM stations, and in this example we were recording the center frequency channel. In addition, we brought this frequency channel to the center of 0 Hz, and we selected this unique channel by low pass filtering as provided by this frequency translating FIR filter. Can we use this knowledge in a more useful framework than multiple FM broadcast stations? Let us consider the example of pagers. Pagers were popular in the 90s. Now they are no longer in use by the general public, but at least in France, these devices are still being used by firefighters or emergency services that cannot rely on public services such as GSM, UMTS, or all these networks of mobile phones that will collapse whenever some dramatic event happens and everyone tries to call. So POCSAG is still being used, and we learned by searching on the internet on the POCSAG Wikipedia webpage that a few channels have been allocated. These are the channels allocated in France, 466 megahertz up to 466.23 megahertz. We see 6 channels over here, and our objective will be to decode POCSAG and these multiple channels. But before we can address multiple channels, as we have just seen using the FM broadcast example, we need to decode one single POCSAG signal. Now, POCSAG is FSCK, so frequency shift keying modulation, which is not very difficult to demodulate, but we need this frequency to voltage converter, the wideband FM receiver, which is actually a phase lock loop, and it's a digital implementation, and to then decode the various bits of the POCSAG messages. But this is already actually taken care of by multimon. Multimon is a tool provided at least on a Unix operating system that will decode radio transmissions, including POCSAG. So rather than including an out-of-tree block that will implement this functionality that is already available, we might as well use it efficiently. So multimon will require that you provide an input file, and this input file can actually be a FIFO, first in, first out, or a named pipe in Unix naming convention. So how do we create this named pipe? We MK FIFO, we create this FIFO. Here we use a writable directory TMP, and we select the file sync over here to point to this FIFO. So this way, the Osmocom source will select a single channel, will demodulate the channel. We're taking the best out of GNU Radio for processing radio frequency signals, and having decoded the signal, we wish to feed it to multimon and its a new generation implementation, which accepts the raw data. So these are short integers, signed integers, as provided by the float to short block, assuming 22 kilosample per second data rate. So here you see that we have selected the data rate of 22 kilosample per second times 64, 64 being the decimation by a factor of 8 over here, and a decimation a factor of 8, which brings us above 1 megasample per second, which is the lower limit of the sampling rate of the Osmocom RTL SDR. So we need to magnify the signal and feed them to the signal processing block. Let us discuss this bandpass filter after demonstrating reception of a POCSAG message. So in this example, here is the Osmocom source with its file sync that we have selected, and in the TMP block we create this FIFO by MK FIFO, and when we run multimon new generation decoder on this file sync by saying that we have a raw input, we disable all decoder -C, we enable the scope, we enable the various POCSAG encodings by adding these decoders to the list of processing steps of multimon, and we will see the spectrum as well as the scope. This data stream will not start prior to both ends of the pipes being connected, so we need to run GNU Radio for the data stream to start. So here is the frequency output of GNU Radio. It's this block over here, this spectrum analyzer. We've just seen one transmission. This is live streaming. I have not edited the video to remove unnecessary times. So now we have run the scope output of multimon, and we wait for some communication to occur. What is going to happen is that this frequency to voltage converter will exhibit some offset. Here is one new communication if the frequency is not at the center frequency of a receiver. So here is, we've seen the preamble with its oscillations, and then we've seen a message which has been decoded by multimon over here. So we've seen one message, here's another message with its preamble first, and then the message that has been decoded again as a sentence by using multimon new generation. So here the objective of this bandpass filter is to remove the DC component on the voltage output of this frequency to voltage converter due to the slight frequency offset between our receiver local oscillator and the transmitter local oscillator. We see here the 4 channels of POCSAG that are widely available in the area. Here is yet another transmission that is not decoded because here we are centered too far from this transmission. So we see here the basic architecture of using this external processing system of multimon connected to a FIFO, which is the output of this file sync of GNU Radio. And by using this FIFO, we can use at best external tools for processing the data. This is the last message that has been transmitted before stopping this analysis. So we see here that this bandpass filter acts as a zero crossing detector. Otherwise, the output here of multimon would be offset, the voltage output would be offset, and would prevent the zero crossing detection, which marks the beginning of a new bit transmission. So once we understand how to decode one multimon instance of a POCSAG single channel, then we've seen that there are at least 6 channels that are active. We've seen 4 of them in the prior spectrum. So now we can just duplicate, this is the power of software-defined radio, adding more channels that not require taking the soldering iron out and analyzing the performance of a new hardware implementation of new reception channels. We just need to copy paste all these channels, replacing the first low pass filter with frequency translating FIR filter instances. So this is what it actually looks like. It might look impressive at first sight, but if we look closely, these are the various channels that we can find in France. So the channel spacing is about 50 kilohertz, and we see that the complete span is less than a megahertz, so well within the sampling frequency of an SDR DVB-T receiver. So the first channel is the low-pass filter, wideband FM receiver, bandpass filter for getting rid of the DC component, and the scaling of the floating point number between minus and plus 1 to a short, assigned 16-bit integer, feeding one multimon new generation instance. And then we copy-paste to a second, a third, and a fourth copy. All these processing steps are exactly the same, except for the first one with its frequency translating FIR filter and its low-pass filter taps defined over here. Again, the same parameters as the low-pass filter over here, a cutoff frequency of 15 kilohertz, a transition width of 20 kilohertz. This transition width reduces the processing power needed. Remember that if I take again the example that we mentioned earlier, if I have a low-pass filter, then the transition width delta F over here as power as a function of frequency will define the bin width that is needed to define this filter, and the number of taps will be sampling frequency divided by delta F, the transition width that we have over here. So it is wise to try to select a low enough transition width so that actually a high enough transition width that will allow to have few enough taps to reduce the computational power. As we are now multiplying the number of analyzed channels, we need to reduce as much as possible the unwanted load due to these various filters. And so each one of these frequency translating FIR filter has a different NCO frequency offset here, which defines which channel is being analyzed. So let us run this flowchart to see how we can decode multiple POCSAG channels. So we see here that we have a first instance with its various names, file names, and we have here the center frequency of the first channel. So these are all the named pipes that we will connect to. So here we create a first FIFO in the TMP directory, and we get ready to connect multimon. Since we've seen earlier that only POCSAG at 1200 bit per second is being transmitted, we activate the raw input, we activate the scope, and we activate POCSAG 1200 on the FIFO TMP1. And we duplicate this FIFO in these three terminals to create FIFO of channel number 2, channel number 3, channel number 4. And we will run 4 copies of multimon new generation. Here we see the scope starting. Of course, each data stream is waiting for the second end of a pipe to be connected. So waiting for GNU Radio to start streaming data. So all these instances of multimon new generation are waiting. And here we start the stream from GNU Radio companion. Here is the spectrum output of this spectrum analyzer here. So we've seen already one communication, middle button, and we keep the maximum value. And here is the first communication. We've seen it every time. The preamble is these periodic oscillations followed by the message being transmitted. So this channel here is mostly maintenance, but here we already start seeing some messages coming in. When there is noise, of course, the scope output is a random signal. Here we've seen the preamble followed by the message, which is immediately decoded by one of the terminals here. We will magnify this guy here because there are some more interesting messages on this channel. Again, here is another message being transmitted, and here is a preamble followed by a message which is immediately decoded. So using this scheme, we see that we can simultaneously decode all 4 channels of POCSAG, only limited by the computational power of this computer. So we see actually here that we have 4 copies of multimon new generation. We have the spectrum analyzer. Each wideband FM demodulator is a thread by itself. So the computational load is becoming significant to run all these decodings. So here is the wideband FM receiver with its audio decimation followed by the bandpass filter to get rid of the DC offset at the output of the frequency to voltage converter made of a wideband FM receiver. So here is a last message being decoded in this instance here with the decoding on the top right terminal. So this demonstrates multi-channel analysis, in this example using POXAG and the pager, which is quite feasible because these are low bandwidth messages, low bandwidth protocols that do not require much processing power. Similarly, another example of multi-channel analysis is ACARS. ACARS is the protocol communicating between planes and airports, and ACARS, similarly as we've just seen, provides multiple channels. In North America, we see here that we have 7 channels within 2.3 megahertz, which is just within the available bandwidth of SDR DVB-T receivers. In North America, you have another set of channels which are separate from this first set of channels. These 4 channels here are 6 megahertz higher, so this will require a second DVB-T receiver to acquire this data in parallel to these 7 channels. In Europe, we receive 3 channels around 131 megahertz, and these are all within less than 300 kilohertz, so these are well received by RTL SDR DVB-T receivers. And finally, we have new secondary channels of ACARS in Europe that require a second DVB-T because they are well above the bandwidth available from these RTL SDR receivers. These frequencies have been collected from ACARS-D website, and here is an example of our own GR ACARS receiver, where we see in this example that we have the hardware source. So in this example, as we're debugging processing of GR ACARS, a new generation, we have a file source that we had recorded on a nearly 2 megahertz bandwidth, 1.15 megahertz. And what you see here is that we are running 2 instances of the ACARS decoder provided on GR ACARS. The novelty of this NG version of GR ACARS is that we have replaced FFTW, the fastest FFT implementation, by GR FFT, as opposed to FFTW, which is not thread safe. You have to take care that only a single instance of FFTW is running at any time. GR FFT is thread safe, meaning that multiple instances of a Fourier transform can run in parallel. This analysis is heavily relying on fast Fourier transform because we're correlating sine waves at 1200 and 2400 hertz with the received messages, and correlation are best implemented through Fourier transforms, as will be seen a bit later in this presentation. So ACARS relies, as all airborne communication, on AM modulation. So here we have an AM demodulation centered on each frequency channel. So here we see here that we centered on 131.7 megahertz, and we have 2 frequency offset by 200 and minus 100 to analyze the 2 channels here separated by 300 kilohertz. And this allows us to collect all the ACARS messages of the planes flying in the area. Here we have a consistent identification immatriculation of a plane, which is found in our ACARS decoding, and you see that ACARS is typically feeding information about fuel consumption, localization of a plane, or this kind of information. So again, the same story as we just demonstrated with POXAG is feasible on ACARS thanks to the thread-safe implementation of GR ACARS for decoding ACARS messages. So we've just seen that we can use this architecture where we have a coarse frequency transposition by the hardware, local oscillator sampling by the A to D converter on the bandwidth of the sampling frequency, and a second transposition to bring any information we might be interested in centered on 0 hertz. But can we use this information differently? The challenge of this IQ detector is that we assume that whatever signal is being mixed with the 2 copies of the I and Q signals are in quadrature. So the assumption is that this oscillator here feeds this mixer to create the I component, and the assumption that is being made is that the quadrature component is a copy of this oscillator shifted by 90 degrees. The practical implementation of analog IQ detector is flawed with these two issues of, if we assume that I is perfect, then Q might exhibit some imbalance in terms of amplitude. The amplitude might not be exactly 1, but this phase shifter might introduce some amplitude variation. And furthermore, it is extremely difficult to keep this 90-degree phase shift on a broadband. If you imagine that you would create this 90-degree by using a length of coaxial cable that would be only at a single frequency, and typical IQ receivers will require that the local oscillator is at twice the frequency so that they can run 2 copies of a clock shifted by 90 degrees following the division of a frequency by a factor of 2. So this means that the I and Q component might exhibit a slight phase shift delta phi here, which are both called IQ imbalance. So if we look at the Sentinel-1 European Space Agency spaceborne radar and its detailed algorithm definition of the level 1 product, which are the outputs of processing level 0 raw IQ data, we are told that Sentinel-1 receiver module performs demodulation in the digital domain so that IQ gain, imbalance, and non-orthogonality are not an issue. So why is it that performing this computation in the digital domain prevents these IQ imbalance issues? Well, if we write in the digital domain cosine and sine, then we write numerically oscillators as cosine of omega t and sine of omega t. In the digital domain, these cosine and sine by definition will be orthogonal because algorithms are not plagued by this imbalance issue. And furthermore, if I implement this I and Q multiplication steps in the digital domain, I have no amplitude imbalance issue because these signals by definition have one unity amplitude. So how can I perform the IQ demodulation that would usually be performed in the analog domain in the digital domain to get rid of this issue of IQ imbalance? What we see here is that in this example, we take the signal from the antenna and we only shift it by using a real mixer here. So we shift the real signal with a real local oscillator, meaning that this signal at the radio frequency band is shifted to baseband, and we assume that Fs, the sampling frequency, is broad enough, is wide enough to clearly overlay all the bandwidth of interest and the mirror image in the negative frequency. Why do we have a mirror image in the negative frequency range? Because this is a real signal that has been mixed with a real local oscillator, meaning that the negative part of the spectrum is the complex conjugate of the positive part, or meaning that the magnitude of a spectrum is an even function. So we necessarily find the copy of the signal in the negative part of the spectrum. On purpose, we have drawn these spectral characteristics as asymmetric to emphasize how these spectral components are shared. So we sample this symmetric spectrum at sampling frequency Fs, and what we can do then is, after sampling this signal, which was shifted by intermediate frequency on purpose, we can now perform a second mixing step using a numerically controlled oscillator at intermediate frequency. So this means that we have initially performed a first mixing step by exponential of j omega LO minus IF t, and then we multiply this with a new exponential of j omega IF, and by taking the product of these two complex exponential, this is equal to exponential of omega, j omega, of course, LO times t. And we are only left with the local oscillator, and we have removed the intermediate frequency intermediate step spectral component. So this is illustrated over here by mixing this A to D output with the IF frequency of this numerically controlled oscillator. We take both spectral components, bringing this spectral component centered on 0. This spectral component, if the sampling frequency is wide enough, is only shifted away from the center frequency. And by taking this low-pass filter here in purple, this is this low-pass filter over here, we get rid of the image and we only keep the original signal. And this original signal here is the baseband copy of the radio frequency signal that was over here, except that this time this signal has been transposed to baseband with a perfect IQ quadrature components, because we have removed the issue of amplitude imbalance and quadrature inorthogonality as described in this Sentinel-1 processing step. So you see here that digital processing allows you to achieve results that could not be achievable using analog electronics. This concept of two-step frequency transposition from radio frequency band to baseband and then from the intermediate frequency to 0 Hertz is actually used in a low-cost vector network analyzer, the Nano VNA, as described in this presentation here. So we've taken the schematic of the Nano VNA, and what we see is that the Nano VNA is actually a free output digital synthesizer creating two spectral components. One spectral component, the radio frequency signal, will probe the device under test, the either reflection coefficient, the S11, by feeding a Wheatstone bridge, or the S21, the transmission coefficient, by feeding the device under test with FRF and receiving the transmitted signal. And what we see here is that when collecting the signal, the mixer, the three mixers that we find over here, are actually fed with a second clock, which is FRF, plus a frequency offset equal to the intermediate frequency. Meaning that the audio frequency, the codec over here, measuring S21 reference signal and S11, are actually fed with some non-zero Hertz signals, which prevent the IQ imbalance issue, because this real mixer here exhibits two spectral components, one at plus FIF and one at minus FIF. And if the sampling rate of the audio frequency codec is large enough, then we will be able to perform the frequency transposition from analog domain to digital domain in on the sample data and avoid the IQ imbalance issue. So what we can read here on the source code of a Nano VNA is actually the frequency offset is equal to 5 kilohertz, and because this codec, this audio frequency sound card codec, is sampling at 48 kilohertz, we see that the 5 kilohertz offset will be using the digital oscillator, the numerically controlled oscillator. The 5 kilohertz signal will be brought to 0 hertz. The minus 5 kilohertz will be shifted to minus 10 kilohertz, and this minus 10 kilohertz will be easily cancelled by using a low-pass filter implemented in the digital domain. So we see here, we can read that the clock 0 is equal to the radio frequency signal, that the clock 1 is equal to the frequency plus the offset, and so the codec here is receiving a signal whose radio frequency component was cancelled by the mixer, and only the intermediate frequency is sampled to be brought to DC by a numerically controlled oscillator, shifting and low-pass filtering as described in DSP.C. This explains the excellent performance of this vector network analyzer despite its low cost at sub €50 price. The performance is very well comparable to a state-of-the-art Rohde-Schwarz vector network analyzer. In its frequency band, we've tested this from a few hundred kilohertz up to 300 megahertz. Newer versions will go higher in frequency, and the performance after proper calibration are well compatible with state-of-the-art Rohde-Schwarz vector network analyzers. So this two-step frequency transposition helped us solve the IQ imbalance issue, the amplitude and a difference between I and Q and the slight phase offset that might remain. This intermediate frequency will also allow us to solve close to DC local oscillator leakage issues that might plague measurements of low frequency spectral components of received signal, radio frequency signal. So local oscillator leakage is described on this chart that was stolen from this microwave journal article that you can find on the web. And actually it highlights an issue that was already met in 1921 by Armstrong when considering the super heterodyne architecture, where he wanted to avoid oscillation of the output stage by introducing an intermediate frequency that would cancel some of the imperfection of the mixers, of the radio frequency mixers. So now that mixers have greatly improved with respect to what we had 100 years ago, the local oscillator leakage is less of an issue when analyzing broadband radio frequency signal. But as will be seen in the next slide, if we want to analyze close to 0 Hertz, close to carrier spectral characteristics, amplitude or phase, then the local oscillator leakage will become an issue. How do we demonstrate this local oscillator leakage? Well, if we take an SDR DVB-T receiver and we look at the close to 0 Hertz, so we significantly decimate. What we see here is that in order to demonstrate the concept, we took an Osmocom source and we decimated once by 8. We decimated a second times over here, and only by zooming in the only by zooming closely on the x-axis can the local oscillator leakage be emphasized. So what we see here is that if we look at a weak signal, slight offset close to 0 Hertz, then this spectral components here is not something that we want to detect. This is the local oscillator leakage at exactly 0 Hertz by definition. What is this local oscillator leakage? It's described here as the local oscillator either being the signal being reflected by the output of the amplifier due to some impedance mismatch, or even worse, some of the oscillator going through the amplifier with its finite isolation, reaching the antenna mismatch and returning back into the amplifier. So this signal at this frequency here, by definition, will be at the same frequency as the signal that is amplified again over here. And if we mix a signal at the local oscillator frequency with another image of its local oscillator, it will create a DC component. So we see here that another example is that this signal being radiated by the antenna, returning to the antenna after being reflected on static targets and going again through the amplifier, so being amplified, will create a DC offset. So all these causes of a local oscillator not being perfectly isolated by the mixer and the amplifier and returning in the mixer will create this DC component, which by definition is centered on 0 Hertz. Now if we analyze the phase of this signal that we want to look at, because this local oscillator leakage is at a frequency offset, then we see in red here the phase information of this signal that is significantly noisy because of this spectral component here. So what we can do to avoid this issue is, in this example, we've introduced a frequency translating FIR filter, which creates the intermediate frequency that was initially introduced by Armstrong in his super heterodyne architecture. And on purpose, we offset the received signal by this intermediate frequency. Again, the only condition is that this intermediate frequency is low enough for both the signal and local oscillator leakage to be within the sampling frequency. Here we have a sampling frequency of 2 megahertz. We have a frequency offset of the intermediate frequency of 200 kilohertz, so that when we shift by 200 kilohertz the whole spectrum using the frequency translating FIR filter, we see here in red that the local oscillator leakage is shifted by 200 200 kilohertz. The signal is then brought to 0 hertz. And by adding this low-pass filter, we made it explicit here so that we can display the frequency transpose signal and the low-pass filter signal. Of course, you could introduce this low-pass filter as the taps of your frequency translating FIR filter here. We see here on the frequency component that now the local oscillator leakage component has been significantly filtered out, and only in blue the signal low-pass filtered is analyzed. And now we have a phase in blue here whose noise has been removed, and we only have here on purpose a slight frequency offset has been left to show the phase rotation every 2 pi, but here we have a clean estimate of a phase in blue. When are we using this kind of analysis of the phase characteristic of a radio frequency oscillator? Here is an experiment that we run in the lab where we wish to characterize the out-of-plane radio frequency surface acoustic wave device vibration amplitude. So we have a device under test. This device under test is a radio frequency bulk acoustic or surface acoustic wave transducer. Bulk acoustic as a resonator like your 8 megahertz quartz oscillator, or radio frequency surface acoustic wave devices for radio frequency filters as you will find in your mobile phone. And we wish to know not only the electrical characteristics, but because these are based on piezoelectric substrates, we wish to know the vibration amplitude of the mechanical wave, the acoustic wave propagating on these piezoelectric substrates. The typical approach is to use a Michelson interferometer where we illuminate with a light beam, a laser beam, the sample, and we wish to know the interference fringes between the direct wave, the reference path of the Michelson interferometer, and the second path that is reflected on this device under test. Now, the challenge with this measurement is that this reference path with respect to the measurement path will be plagued by some static phase variation due to the environment, temperature, moisture, all kind of effects that change the optical index of air. So the classical approach, similar to the super heterodyne measurement technique, is to introduce a frequency offset, in this case this acousto-optic modulator running at 80 megahertz will shift the frequency from the helium neon laser by 80 megahertz prior to illuminating the sample over here, and the sample reflected signal goes back to through the acousto-optic modulator to be shifted by another 80 megahertz, so 2 times 80 is 160 megahertz. This signal will be reflected on the front lens of the laser acting as a mirror, and the reflected signal will be reflected in the beam splitter to interfere with the direct signal coming from the helium neon laser, the length of the path here being shorter than the coherence length of the laser. So on the radio frequency step, what we would usually do is collect this optical signal that has been shifted by 2 times 80 megahertz, so that's 160 megahertz, plus the frequency of the vibrating sample here, the radio frequency sample that is being analyzed. And we wish to detect the phase and magnitude of this information. How do we detect this? Well, we can detect this by analyzing the output of a photodiode directly measured at twice the omega output of the acousto-optic modulator. And if we mix this output with the signal that was used to drive the sample over here, then we will shift 2 times omega 0 plus omega minus omega, the frequency driving the signal, brings us back to 2 times omega 0. So here we have a carrier frequency, which is the reflected intensity from the sample. The carrier frequency is simply the signal that went twice through the acousto-optic modulator without considering the vibration amplitude. This is representative only of the reflected intensity, reflectance of a signal. And then we have the signal that has been shifted by omega, the operating frequency of this device, and that is electrically shifted by another omega to bring it back to 2 omega 0. And your classical measurement would use the lock-in amplifier to detect this phase and magnitude. Here is a picture of the experiment with its two spectrum analyzer, its two synthesizer, the lock-in amplifier, a fancy experiment. We wish to get rid of all these equipment that our colleagues will steal whenever we are not using the experiment, and replace all this expensive hardware with a B210 dual channel software-defined radio receiver. So you see that all this hardware is actually replaced by software-defined radio processing, where we will collect channel 1 and channel 2 of the two channels of the B210. We will display magnitude of channel 1, magnitude of channel 2 as the sideband and the carrier frequency magnitudes, and the ratio of these two quantities will give us the vibration of the sample, and the phase of the ratio of these two quantities, of these two complex quantities, will give us the phase difference between the reference and the sideband, and hence the phase of the acoustic wave, which is related to the acoustic velocity. So in this example, we not only bring the flexibility of software-defined radio by tuning the parameters whenever we run a new experiment. We have a radio frequency front end with a very broad spectral range, 70 to 6,000 megahertz, and we will be analyzing the signal as the sample is moved under the optical microscope here. So we will map the acoustic field by scanning, by raster scanning the sample under the table. So this brings us to the actual signal processing flowchart. We have here the USRP source of the B210. Because we wish to get rid of the noise that we have just addressed of the phase measurement, we have these two frequency translating FIR filter acting as heterodyne measurement, and we will display the complex to magnitude. So we will display the magnitude above spectral component, as well as here is the division, that's the division of the two spectral components, which will give us the phase output, so hence the phase difference between these two harmonic components, and all this data will be streamed to the laptop collecting the data. Why do we actually stream the data? Because we need to synchronize the data stream that is generated by GNU Radio with the positioning table that scans the sample under the optical microscope lens here. Now, GNU Radio could handle stage positioning, and we will see in the next slides that we believe that the most efficient approach is to share resources between GNU Radio running processing, radio frequency processing steps, and external software. In this case, this is GNU Octave. GNU Octave has an instrument control toolbox, and this instrument control can communicate through a serial link with, for example, this positioner stage. So in this example, which will be described further in the next slides, here we use the streaming procedure of 0MQ. 0MQ is a UDP-like data stream that will send data from GNU Radio to the laptop. Whenever the Octave software is ready to process data, it will receive data for further processing. If the stage is being moved, then the data are irrelevant, if only because the stage is not in a static position, and the data will just be lost and not be neither collected nor processed. And here we see that whenever we are not collecting data, we will send the command to the table for moving the sample and raster scanning. So here is an example of sharing processing, radio frequency processing using GNU Radio, and data processing or instrument control using GNU Octave. So here are some examples. This is a bulk acoustic resonator, typically like the one you would find in microcontrollers for generating the 8 or 16 megahertz reference clock of microcontroller. This is the carrier signal, optical carrier, which is the reflectivity. Here we see the keyhole-like electrode on a piezoelectric substrate, in this case quartz. Here we have a sum of acoustic vibration plus the reflectivity, and here we divide this measurement by this one, so we get rid of the reflectivity and we only get the magnitude and the phase of the acoustic wave propagating in the piezoelectric substrate, defining the frequency of the resonator. These are overtones, so if you look at some of the spurious modes, you see these nice patterns here. Again, carrier frequency, vibration plus carrier, and by taking the ratio of these two quantities, acoustic field, magnitude, and phase. We can do the same with surface acoustic wave device. These are 444 resonators used as temperature sensors. You would find the same in filters, in the 444 megahertz ISM band filters. This is the reflectivity, so the pattern of two parallel resonators. The first resonator at 433 megahertz, the 434 megahertz, the first resonator at 433. How do I know which one is which? By looking at the electrical signal, I get both responses because these two resonators are in parallel, but by mapping the acoustic field, I see here that by probing this surface acoustic wave device at 433 megahertz, I get energy in this resonator here, and by probing at 444 megahertz, I get energy in this resonator here. Interestingly enough, if I look at a spurious mode at 432 megahertz, I see that the energy is in this resonator here, so the one closest to 433. So this allows us not only to identify the cause of spurious modes, but possibly also to alter the geometry of surface acoustic wave filters by knowing where the energy is concentrated. If we map the phase as a function of position along the electrodes, we see here the standing wave pattern in the Bragg mirrors on the sides of a resonator or in the interdigitated transducers, and where the acoustic wave is propagating, the phase is 2 pi f tau, f the frequency, tau the time delay, so that the phase here provides the acoustic velocity, because tau is d over v, the distance that has been traveled by the acoustic wave divided by its velocity. So here we see that from the slope of a phase as a function of position, we can deduce the velocity of the acoustic wave, which closely matches the 3,100 meter per second, well known for the Rayleigh wave on piezoelectric substrate made of quartz. So here you see how we can make a lab experiment using software-defined radio after getting rid of the local oscillator leakage that would otherwise prevent a fine measurement of the phase information at the output of this measurement. So not only does sharing resources between GNU Radio and GNU Octave allow for taking the best of the two worlds, the radio frequency processing from GNU Radio and signal processing or instrument control from Octave, but also this will allow us to only analyze bursts of data and not necessarily continuous streams, thanks to the 0MQ publish subscribe streaming mechanism. This is an example of a noise radar that was implemented using two radio frequency system. In this example, we use either a Wi-Fi dongle or a Pluto SDR as a pseudo-random signal source, and this pseudo-random signal source is recorded by a B210. So the B210 Etus Research software-defined radio is a dual-channel coherent receiver. One of the outputs of a random source, whether the Pluto SDR or the Wi-Fi dongle, is stored by one channel of the B210, and the second channel will record whatever is collected by an antenna. And if some targets are visible in front of a radio frequency emitter, we will be able, by using correlation between the recorded signal, we do not know what the Wi-Fi signal or the Pluto SDR pseudo-random stream is emitting, but by recording the signal, we will be able to detect time-delayed copies of the signal that has been emitted in the receiver. Remember, a correlation is written, the cross-correlation between a reference signal X and a surveillance signal, so the received signal S, is defined as the time delayed copy of X with respect to T. So we take the reference signal that was transmitted and we shift it over time to try to find copies of S in X. And how do we find copies? Well, usually X and S are mean zero value, meaning that their product here will be alternatively positive or negative. And one way of detecting the amount of energy in the product of X times S is to take the integral over time, let's say from minus infinity to plus infinity over time. And this is the correlation. So the cross correlation allows us to find, it's a match filter for finding time delayed copies of S in X. So usually the mean value of the correlation will be equal to 0 if the mean value of x and the mean value of s are equal to 0, except if x and s match. If x and s match, well, then in this case you will have x, which is a randomly varying signal. S will be time delayed copies of this signal x. But if these two match, so if the time delay tau brings this signal to match, then the positive part of x will match the positive part of s, the negative part of x will match the negative part of s, and taking the product of these two guys will create minus times minus is positive, or we will get positive times positive, which is a positive component, and this integral here will end up accumulating energy if tau is selected so that the two components x at x of t plus tau match s. So this is what cross correlation is about, trying to find this time delay tau so that the two quantities match and accumulate energy coherently. So this is how radar is implemented. We send a noisy signal. This noisy signal reflects on the target, is received on the receiver side, and only when the right time delay is detected by using the correlation will we have a non-null correlation output. Now we can do better by sweeping the receiving antenna over distance, so we can complement the range, which is the distance of the source to the target, by complementing with azimuth information, and this is called synthetic aperture radar. In a synthetic aperture radar, we repeat the measurement by sweeping the position of the receiving antenna along a linear path, and by taking the correlation of these time domain signal at various positions, we can demonstrate that we can not only compress the pulse in the range direction, but also in the azimuth direction, and have a localization of the target with an angle resolution determined by the length of the rail here of this ground-based synthetic aperture radar, GBSAR. So if we only focus on the range resolution, the range resolution is determined by the ability to finely detect the position of this pulse in the time domain. So this is time over here, and what we wish is to finely detect in the time domain when this pulse is located. Now we can intuitively think that the time resolution here will be given as 1 over the bandwidth of the signal B. The bandwidth B is the spectral spreading of the transmitted signal, and the time resolution will be given as the inverse of the bandwidth. So that if we have a two-way trip, well, the range resolution will be inverse of twice the bandwidth. That's simply because the radar signal will go from the transmitter to the target and then back to the receiver. So that's half of the two-way trip that we measure, and we convert the time of flight into a range by multiplying by the speed of light, C0, 300 meters per microsecond. So the range resolution is C0 over 2b. Now this means that we wish to maximize the bandwidth B of the signal being transmitted to maximize the range resolution, to improve the range resolution. However, the second challenge is that the data storage of this radar system is B, the bandwidth, time S, the size of each item. So if we consider that we are storing the complex numbers at the output of the USRP, then we have 8 bytes for each complex number. We have I and Q components, which are each floating point number, and each floating point number is encoded on 4 bytes. So this means that we have 8 bytes per sample, and you see here that we are measuring the reference and the surveillance channel, meaning that we have 2 channels. So we have 2.4 megasample per second, which is the maximum that we can be achieved using a cheap RTL SDR DVB-T dongle, multiplied by 2 channels, multiplied by the number of bytes per complex, so that's 2.4 mega complex per second multiplied by 2 channels. So if we want the data rate per minute, we multiply this quantity and we find 2.3 gigabytes per minute. So this is a huge amount of information to store if we want to measure a few minutes worth of radar measurements. And the challenge here is that this motion of the antenna along its rail, first of all, will not benefit from any measurement as the antenna is moving from one step to another, because as the antenna is moving, the signal is unstable, so there is no point in recording this data. And furthermore, we only need to collect a burst of data when the antenna is stable and not as it is moving. And here the screw that is moving an antenna means that the antenna will require about half an hour to move along this 1.2 meter path length. So this would mean that we would record about 100 gigabytes with only very few samples being worth collecting. So what we will consider now is how to best use external software, in this case streaming the 0MQ data so that GNU Octave can fetch the data only when the antenna is stable, and furthermore so that GNU Octave can control the motor here to give the order for the antenna motion whenever data have been collected. So rather than demonstrate the concept on a full-fledged radar system, let us demonstrate on this much more simple data stream. In this synthetic signal example, we have created two signal sources, two sine waves, whose frequency is defined by a queued graphical user interface range, so that's a slider, and we will display the frequency output from GNU Radio. What we will do is we are going to interleave these two data sets, throttle because there is no hardware means for GNU Radio to know what is the data rate, and we will send this to a 0MQ publish sync. You will see that this publish sync will act similarly to UDP, meaning that the data will be transferred and lost if there is no listener, or will be received by GNU Octave. In GNU Octave, a 0MQ library allows you to open such a socket. We need to have a consistent data rate. So here we have a sampling frequency of 1 megasample per second, consistent with the 1 megasample per second over here. And we will see that we stream 2048 data chunks, which is consistent with a vector length of 2048 sample over here. We open the socket, we collect data from port 5555, which is consistent with the port that we have opened here. We fetch the data. Sometimes the data blocks will be smaller than the expected length, and so we loop until we get the right number of data. In this example, we will plot the spectrum of the data that has been transferred. So let us demonstrate this concept on an actual flowchart. So here we have prepared two signal sources, which are defined by the FLO, the local oscillator, frequency defined as range over here, and we stream the data to a 0MQ publish sync. So here we've defined the local host 127.0.0.1 as the IP address with port 5555, which is the same as this GNU Octave script, where we have the sampling frequency, the number of data that are collected, and here we see that we connect to the local host port 5555, which matches. So if we run the GNU Radio flowchart here, we see that indeed we have our two frequencies which can be shifted, and we see that even if there is no Octave listening at the data stream, the flowchart is still running, as opposed to the previous example when we were running the FIFO, where both ends of the pipe had to be connected for the data to start streaming. And if in this example we start Octave, we see that we have a tick and a tock, so we have a duration of the execution. And if we start moving the data over here, we see that indeed we have both quantities shifting at the same time. So we demonstrate the real-time data streaming from Octave to from GNU Radio to Octave, and indeed the ability to fetch the data and process the data, in this case by taking the Fourier transform of the signal to display the spectrum. Now maybe we want to do something a bit more interesting than just displaying the spectrum, because this was just designed to demonstrate that consistent data could be streamed from GNU Radio to Octave. So if we go back to this presentation, but rather than having two sine waves which have no timing capability, we replace these with correlation sources. So now we can try to replace the signal source as a sine wave with a noise source. So let us go back to GNU Radio. And in this case here, we see that we've replaced the same data stream, except that this time we have a noise source. So a noise source with bandwidth B will allow us to find the time delay with a single beam width, because a noise only correlates at 0 time offset with a beam width of 1, so inverse of a bandwidth. And we will create what would a radar introduce a time delayed copy. So this is a noise, but what is important is that this noise is known, and this known noise source will be delayed by a time delay n, which is defined by this queued graphical user interface range, which is the same n than over here. So we interleave again the noise source with the delayed copy, and what we will do is this time in Octave, rather than plotting the spectrum, which is of little interest in a noise source, we will display the correlation. So again, we fetch at sampling frequency consistent with the flowchart in GNU Radio, and this time what we see is we connect again to 001 5555 port. We fetch the streams, but this time we will run the cross correlation. So the cross correlation will be the match filter to search for time delayed copies of the noise in the reference signal. So if we run this flowchart, we have the time domain display. This is the time sink, and we can actually run the correlation in Octave by running this demo script, and by running the sampling here. So this is the time domain output, and now we can run the correlation on GNU Octave. So by looking at this script that we just described earlier, where we have collecting the data from localhost 127.0.0.1 port 5555. We fetch the data, and once we've created the two vectors, which are the de-interleaved data sets, we plot the magnitude of a cross correlation. Because vector 1 and vector 2 are complex numbers, the correlation will be a complex number when we plot the magnitude. So by running this script, we see here that we have a correlation peak, and if we offset this time the time delay, we see that the correlation peak is indeed moving in the x-axis, with the x-axis providing the time delay for the reference signal to match the transmitted signal. So we see here that we can finally detect the time delay between the reference and the measurement, and the beam width is equal to one sample. So this unique sample is determined by the bandwidth of the signal that is being transmitted. So we wish to compare maybe this correlation output from Octave with the output of GNU Radio. How could we compute the correlation, since GNU Radio does not provide a correlation function? Well, we've just seen earlier that the correlation between a signal X and a signal Y as a function of time delay tau is looking for time delayed copies of Y in T, so looking at Y of T plus tau within X, and finding the similarity is achieved by taking the integral from -infinity to infinity as a function of time, with energy accumulating coherently if the two signals match. Now we can compare this expression with a convolution between X and Y of two signals as a function of tau, and the convolution is the integral between infinity of x of t, and this time y of tau minus t dt. Now, why is this useful? Because convolution can be quite easily expressed as the Fourier transform of a convolution between x and y is actually equal to the Fourier transform of x multiplied by the Fourier transform of y. And this means that we can benefit from the n log n computational complexity of a fast Fourier transform and perform a convolution as the product of two Fourier transforms. So how is this related to a correlation? Well, we quite easily see that between correlation and convolution, the only difference is that in one case we have t plus tau, the other case is tau minus t, meaning that we need to flip the time of the argument. So if we don't want to have a Fourier transform of convolution, but the correlation between x and y, we need to find a way to flip time as found here in the convolution. How do you flip time? If you want to go from exponential of j omega t to exponential of minus j omega t, the solution is quite obvious. We need to take the complex conjugate of this quantity, meaning that we take the complex conjugate of the Fourier transform. So the Fourier transform of a correlation between x and y is equal to the Fourier transform of x multiplied by the complex conjugate of the Fourier transform of y. So let's see how this compares with the output of Octave between Octave and GNU Radio. So we have prepared this flowchart here where you find again the noise source, time delayed, interleave, throttle, stream to vector, feeding the 0MQ sink here. And what we did now is we added these fast Fourier transforms to perform the Fourier transform of the reference channel and the Fourier transform of the time delayed copies. Multiplied conjugate, this is all performed on data chunks of length m being the same length as the data that are streamed through 0MQ. And once we've performed the complex conjugate multiply with length m, we go back to the original time domain by taking the inverse Fourier transform, back to stream, magnitude, and time sink. Now actually notice that we take first the reverse Fourier transforms and then the forward Fourier transform. This is just a matter of convention as to where the zero is located, if it's on the side or on the center of the Fourier transform. This trick allows to have the center frequency on the at the zero delay. So if we run this data stream here, we see now that we indeed have the time domain plot on top, and even if there is no GNU Octave running, we see that still 0MQ is streaming data that are not being analyzed, and here we have a time domain delay between the reference and the measurement. And if we now run this simultaneously in GNU Octave, we see that indeed if I move one data set, both data sets are moving. Actually, we see that Octave is moving in the opposite direction than GNU Radio. This simply means that we have swapped the reference and the measurement channel. That's easy enough. We can just stop the data stream here and swap both channels so that they match. So if we replace the reference channel and the measurement channel here, we will see that we can match the behavior of Octave. So we restart GNU Octave over here, and this time we see that if we increase time, both charts will go to the left, and if we go back in the other direction, we center again both components. So we see that there is a close match. Actually, that's quite expected, since if we read the source code of a cross correlation of Octave, we will see that this implementation is actually exactly what is running in Octave. Octave cross correlation function is actually Fourier transform, multiply conjugate, and inverse Fourier transform. So this concludes the presentation, where we emphasize the benefit of using, on the one hand, Octave for performing. You see that the cross correlation here is completed in GNU Octave. Here is the demonstration that we just did on the Fourier transform of a cross correlation between the Fourier transform of x multiplied by the complex conjugate of the Fourier transform of y. Here is the correlation blocks, and here is the streaming of data to GNU Octave, and we've seen the close match between GNU Radio and Octave. So this concludes the presentation on using external tools to best use GNU Radio. Here we wanted to show how you can optimize the bandwidth by analyzing all the data that were found within the baseband. We've seen that actually radio frequency does not matter, only bandwidth matters, and actually this also defines what kind of protocol can be addressed using software-defined radio, limited by the bandwidth of the sampling frequency and the signal that has been spectrum spread by introducing information. We've seen that we can efficiently use external tools, and this means that maybe it's worth considering whether writing a new out-of-tree block is the best solution with respect to using external data tools. And here we've illustrated streaming through 0MQ data to GNU Octave. Here is a demonstration of passive radar using a Wi-Fi non-cooperative source. Here is my balcony. I was streaming Wi-Fi signals, not for streaming actual data, but for illuminating buildings. These are buildings opposite to my balcony whose reflections are detected by cross-correlating the transmitted data with the reflected data. This has been presented at the GRCon in 2020. With this conclusion, I thank you for your attention and hope you will enjoy playing both with GNU Radio and GNU Octave.